Hello. Today I'm going to be doing a hopefully brief presentation on urban environments and how they both interact with and help cause some of the weather and climate effects that we see. So I'm going to give you a brief background to begin. First, what is climate change? I'm sure you've heard of it in your classes or in the media or just having conversations with your peers. Climate is defined as the statistical properties of atmospheric variables like temperature, precipitation, and wind over a long period of time. So, long period of time is going to be the key here. Climate change is the change in that statistical property. So, say our statistical property was mean temperature, then a change in mean temperature, whether it be monthly mean temperature, annual mean temperature, that's climate change. So then what's the difference between weather and climate? Weather is something that's immediate. It's your day-to-day. What's the temperature right now? What's the high temperature today? What's the low temperature today? Whereas climate is that long term. So to put it in like a metaphor, weather's your mood and climate's your personality. Weather is how a baseball player performed in the game today, and climate's how he usually performs. Weather is what your outfit is today, and climate's your style. It's everything you have in your closet. Climate is what you can expect, and then weather is what you actually get. So, how does climate change? Climate can change in a variety of natural ways, including Milankovitch cycles, volcanic eruptions, sunspots. We'll go into all of those. However, not all of Earth's changing climate can be attributed to natural means, and instead can be directly attributed to humans. We call this anthropogenic or human-caused climate change. So we'll talk about the sunspots first. So when we're talking about sunspots, what we're really concerned about is changes in solar output, because that solar radiation, changes in that is going to change how much Earth receives, which will change the amount of heat we get. So we see that there's about a 0.1 to 0.2% change due to sunspots or lack thereof, and it's about an 11-year cycle. So the Maunder minimum was a period of very few sunspots and lower solar activity. This occurred around the year 1600, which is also around the period that the Little Ice Age occurred. So we do see that there is a correlation. So on this one, I want to orient you to this. The red line here is temperature. The blue line here is your solar radiation. So what we see is after the year like 1960-ish, there's a steady increase in temperature. This is an 11-year average. The lighter red is the yearly, but the average is going up, whereas the average of the solar radiation is actually decreasing. So we can't just say that an increase of solar radiation is causing the increase in temperature that we're seeing. There must be something else going on. So let's see what other causes there could be. So we could also have changes in Earth's orbit. So the Milankovitch cycles refer to the regular natural variation in Earth's orbit around the sun. Your classes have lied to you. We are not always rotating at exactly 23.5 degrees. We don't go around a perfect orbit. There's different, Earth wobbles. But the changes that we're talking about, they take place over tens of thousands of years. So obliquity is one of these. It takes 41,000 years. That's the period of that one. Eccentricity is a 100,000 year period, and precession is a 27,000 year period. So obviously these changes take place over like very long periods of time, whereas what I was just talking about was only the span of 40 or so years. So another way that we think about climate is the appearance of aerosols. So aerosols and greenhouse gases, they are gases or particles that are in our atmosphere. So here we have our atmospheric carbon dioxide concentration on the top, and then our temperature variations on the bottom. And what we see is they vary pretty similarly, right? We have this decrease in temperature that corresponds with a decrease in CO2 concentrations, rapid increase. We use ice core analysis for these 400,000 years before present because obviously we weren't there to record that. So we have to use ice core analysis. They drill down into the ice and they're able to analyze the gas trapped in the ice to figure out what the CO2 concentration was. Now, what I want to bring your attention to is the present. So we can see that there was a natural variation in the past. You see like, oh, here's 280. Then we had a low of maybe 180, and it goes up and down and up and down. We see the same thing with our temperatures. But if we come to the present, we see a very, very rapid change. It doesn't go back down, and even if we were at this peak, we are now well over, we're approaching 400. I think we're over 400 parts per million today. Whereas in the past, we were never above like 300. So that's a very rapid change. So we're seeing increasing temperatures associated with that as well. Now, since this has only occurred basically since the Industrial Revolution, it is safe to say that that is human caused. Whereas in the past, these natural fluctuations can be attributed mainly to natural causes. Now I'll go back into some other natural causes. So changes in land configuration and surface characteristics will change the climate. So plate tectonics naturally change the configuration of mountains and oceans. Those will affect the climate. But also human land use changes through deforestation, urbanization, which is what we're going to be focusing on, and desertification. Those will all change our climate as well. And then there's the aerosols when it comes to volcanic gases. So volcanic eruptions inject aerosols high into the atmosphere, which is going to block your incoming solar radiation, which will lead to temporary cooling. Human-produced aerosols like soot will also affect the reflective and absorptivity of energy in the atmosphere. So I'm going to go back to the greenhouse gases for a second because they're very important. So two things keep our planet warm enough to sustain life: solar radiation and the greenhouse effect. We need the greenhouse effect. So what happens is solar radiation will pass through the atmosphere. It will get absorbed by the surface of the Earth, some of it, and then re-emitted as heat. That heat is then emitted to the atmosphere. When it encounters greenhouse gases, it will be re-emitted back down towards the Earth. So it's acting like a greenhouse, right? It's trapping in that heat. We need that. Otherwise, it would be very, very, very cold, and we would not be able to live here. However, when we have a higher concentration of greenhouse gases, that leads to more and more heat being trapped, which is going to lead to a warmer and warmer Earth. Too much warming will change the climate that we know. So here's, that got pixelated, but it's okay. This is a energy diagram, so we can see that there's the incoming solar radiation. Some of it is reflected by the clouds in the atmosphere, and that comes out. Some of it's reflected by the surface. That goes into this 137. Now some of it's absorbed by the surface and then re-emitted in a series of different things. So it's re-emitted. It can be reflected again, or it can be, once it's absorbed by these greenhouse gases, it can be sent back out to space again. And there's, of course, more complicated processes at work here, but I won't go into those right now. Here's another concentration of greenhouse gases. So from year 0 to the year 2005. So we can see that there is a natural change. We see it up and down. But what happens here? That's very different, isn't it? Goes way up. And it's not what we've seen in the past. Like I said, I think we're over 400 parts per million now. Whereas in the past, 275, 280, very different. Why should you care? You live here. You should care. Changing climate will affect literally every single aspect of human life here. So climate change can cause increasing air pollution and allergens, which can affect people with asthma. It'll cause increased risks of cardiovascular disease, respiratory allergies. You'll have extreme heat, like I've been talking about. That can lead to heat-related illness and death, cardiovascular failure. Severe weather, we've seen an increase in certain severe weather events, and I'll talk about that, which leads to more injuries, fatalities, loss of property, and of course there's mental health impacts associated with that as well. Then you have your, I would say, run-of-the-mill environmental degradation. That's still a big deal. That's going to cause migration, civil conflict, again, mental health, loss of jobs, income. There's also social effects. You'll see more social inequality. The social inequality that exists will only be exacerbated by this, again, with like health inequalities as well. Um, you'll have water and food supply, malnutrition, um, eating bad food. And then there's also water quality impacts. So cholera and other diseases that are waterborne you can see an increase of these due to climate change because of all these different aspects of climate change. It's not just rising temperature, it's rising sea level, it's increased air pollution, etc. So there's a few ways we talk about climate change. It's not just a shifted mean, so that's one way we talk about it, as if the mean actually shifted. So in this case, the solid curve is the normal case, and then the dashed curve is the climate change case. So in a shifted mean, the whole curve shifts right. So you're going to see less cold weather, less extreme cold, more hot, more extreme. Then you can talk about increased variability. So the probability of the mean goes down, but you can see there's going to be more extreme and more extreme. So the stuff on the edges is going to get more common. And then you can also talk about changed symmetry. So that's when you're going to see it goes off kilter, right? So it's no longer a perfectly normal curve anymore. All of those count as climate change, since the climate is changing. So, why am I talking to you about this in an urban class? Because we're getting to the urban effects now. So, urban has an effect on climate, and climate change has an impact on urban areas. This is because everything works at a series of scales, and all the scales interact with each other. So, the urban climate is going to have effects on the local climate. The local climate has effects on the regional, and the regional has effects on the global climate. Same thing happens in reverse. Your global climate is going to have impacts on the regional, the local, and the urban climate, respectively. Here's the water cycle. So this was the old water cycle. I'm sure you're familiar with some version of this. You have your precipitation, your condensation, your evaporation, and you see a little bit more specified groundwater flow, snowmelt. What's missing from this diagram, do you think? I don't see humans anywhere. I don't see the Walmart parking lot. Where's the Walmart parking lot? That's going to change how the water cycle works, isn't it? So they actually did release a new water cycle diagram very recently. So if you haven't seen this one, this is the new and updated one. And it is the first one to specifically show human use. So we can see urban runoff, municipal water use, domestic water use, industrial water use. All of these are very important to the water cycle. So it's very important that they're represented here. So why do urban places have different climates? In order to get into that, I need to introduce a few key terms. I don't want to assume anybody knows anything. So first we have specific heat. This is the heat required to raise the temperature of a unit mass of a substance by a given amount, usually 1 degree. We'll get to that and why that's important. Your next term is latent heat. That's the energy that goes to changing the phase of a substance. So for example, liquid to solid. Processes like condensation release latent heat. Processes like evaporation absorb latent heat. This is actually the reason why you feel cool when you sweat. It's not because the water's cooling you off. It's the evaporation of your sweat that's cooling you off. It's absorbing latent heat from the surrounding air and from your body, and that's going to cool you down. Your next one is albedo. Albedo is the ratio of energy reflected by a surface to the amount that it received. So basically, it's a measure of reflectance. Forests are dark, but urban surfaces are very, very dark. This is important. So I'm going to go over a few albedos just so you can see what I'm talking about. So stuff like vegetation has an albedo of 17 if it's short and green, a forest around 17, something that's dry 25. Higher albedo means more reflected, so less absorbed, which means less heat. So ice has fresh dry snow is your highest albedo, around 80. So that means 80% of your incoming solar radiation is reflected. But let's look at our bare surfaces. Our concrete pavement is 20. Our asphalt pavement is only 7. So when we have these natural surfaces like forests and fields that are turned to stone and concrete and asphalt, there's a change in the reflectivity in the albedo and in your heat capacity. So when we have these changes in urban surfaces, there's a few things. There's an irradiative change, or a radiative change, sorry. You see a lower albedo, so a lower reflection, which means you're going to have more absorbed. And when there's more absorbed, you're going to have more heat emitted. You also have an obstructed horizon. We call this the sky view factor. When you can't see the horizon, or when there's buildings and trees blocking your way, that heat is going to have less chance to escape. It's going to be blocked. Same thing with the walls of your city. There's going to be reflection between walls, and the more surfaces it hits, the better chance for that heat or that radiation to be absorbed. You also have a thermal change. So the specific heat properties of asphalt and something like a leaf are very, very different. You're going to have massive heat storage in these cities. There's also a moisture change. There's less moisture and evaporation. And when we were talking about evaporation, we associated that with absorbing latent heat. So that energy that would have been taken out of the atmosphere, that heat that would have been taken out of the atmosphere with evaporation, doesn't happen as much. There's also a change in roughness, so obstacles such as buildings will increase your turbulent transport. We'll talk about that a little bit when it comes to weather. And then emissions, so aerosols and greenhouse gases from industry, cars, all of that will affect your radiative transfer. Aerosols can also act as condensation nuclei, so rain, water, it can't condense onto itself. It has to have something to condense onto, and we call those condensation nuclei. So aerosols can provide that condensation nuclei. It can provide something for water to condense onto. We'll talk about that again when we get to weather. So let's look at an energy balance for a rural situation and an urban situation. So QI is our solar radiation that's incoming. So it's the same in both cases. Now we look at our reflected. Big difference here, isn't there? Our reflected in the rural case is 1.9, but our reflected in the urban case is only 0.4. I'm going to skip the infrared term. I'm going to go to your latent heat. So latent heat release, so this is stuff that's going out, is 2. This is less in the urban case. So you have less heat escaping, less latent heat escaping in your urban case. There's also this storage heat term. We only see it as 0.3 here in the rural case, but that's 1.3 here. Also, we have a new term over here, anthropogenic heat. That's that heat that's caused from cars, your AC running, all of that's anthropogenic heat. We don't have that over here. So what we see is actually a net down instead of a balance. Here's the urban heat island of Atlanta. So up here, this is just a colorized like satellite image of the like land use. So the gray obviously is like your gray surfaces, roads, buildings, and the green you have your green surfaces. This bottom image here is an infrared imagery. So red is hotter, your yellow areas are colder. They line up pretty precisely. You can see very well your roads here, your buildings. They line pretty well. Here's your urban heat profile. So if you have rural, maybe you're at 85. You go to downtown, you're up to 92. You have Celsius over here if you prefer that. But there's also a second peak with your suburban. So maybe you had some kind of tree, a park maybe, and you went back down to 86, 88, around 30 degrees Celsius. But then you have a second peak once you get to that suburban because it's more urbanized landscape, and you get back up to around 31 Celsius. So here's your thermal infrared imagery again, a little bit more high resolution. So you can see your trees and your parks here, especially, those are appearing as this blue, green, and yellow, but your buildings, your streets, and your other surfaces appear as red. We're even seeing some of this white, which is really hot. Here's the suburban area, more green than your urban area, but you can still very clearly see the roads. I would bet these are probably neighborhoods. So those are very clear. They pop out as well. So, urban heat islands. These I talked about briefly in one of my discussion posts, but when your city cores are warmer than your surrounding rural environments, it's sometimes up to 10 degrees Celsius. So that's around 20 degrees Fahrenheit. It's most prominent under clear skies, low wind conditions, and they're most prominent at nighttime, but they can occur throughout the year and throughout the day as well. So I want to talk about a few different kinds of urban heat islands. So there's also a hydrological urban heat island. This is when you have stuff with hot runoff. So you have rainfall, it interacts with a very hot surface like an asphalt parking lot maybe, and then it goes into a storm system, still very warm, and when it merges with that urban stream, it's still warm and it's going to very abruptly change that water temperature. That can harm a lot of aquatic ecosystems, both fisheries and plants in the region. There's also a racialized urban heat island. So communities of color in Atlanta experience differential exposure to heat. So this map here shows you the daytime heat clusters in the Atlanta metro, and then also where the different races live. So this is the whole area. Then you have the HOLC boundary in red here. So this is the whole Atlanta metro. And then the areas that are classified as white majority, mostly yellow, which is our coldest, classified as black majority. We see a bit more red here pop up. Asian, still red, and then Latino, also red. So what we see is that this heat effect disproportionately affects people of color. There's also some precipitation implications. So this is what I was talking about with the changes in wind. So because of the very rough surface of the city, air is going to tend to move toward the city on all sides. So when it's a very slow wind day, there's going to be a greater urban heat island, like I talked about with the low winds. So what we have is a thermal expansion of the city, so that creates almost like a localized low pressure over the city, and air moves in to fill that low, and when it moves in, it can't go down because that's where the surface is, so it has to go up. So it's going to create convergence and lift, which leads to clouds and precipitation. There's winds aloft, so those can blow those clouds in that precipitating region well beyond the city proper. So These effects can also disrupt and even enhance certain precipitation and weather patterns that already exist. So if a front moves through the area, maybe we see a particular cell become stronger as it passes over Atlanta. So this one's called beef or pork snow. So the National Weather Service Dodge City area documented localized downwind snow, which was attributed to animal slaughterhouses and power plants. They provided the cloud condensation nuclei needed for this precipitation event. Also, the heat needed for that additional convection to occur. So this is the wind direction we saw that day, and then the stars here are your slaughter plants. This blue here is the radar imagery, so you can see this plume of snow. And then you can also see it on satellite the next day. This lighter white area is that snowfall. So let's talk about severe weather and what happens and how they affect cities. So, can tornadoes hit cities? Yes, they can, and they do. There's a myth that tornadoes don't hit cities or that they can't hit cities, but they can, and they do. Such as the Atlanta tornado. This was an EF2 tornado that hit Atlanta in 2008. So this is where it touched down over here, and then it moved over the center of the World Congress Center, right through downtown Atlanta, before it lifted over here. Here, this is called a storm relative velocity. So green and red are in opposite directions relative to the radar, and this is called a velocity couplet. So basically, I don't have a pencil with me, but if you have one thing moving one way and another thing moving another way, you can try it with a pencil. Put a pencil between your two hands. That's going to spin that, and it's evident of a tornado. So here we can see there is a tornado right there in downtown Atlanta. All right, let's talk about this expanding bullseye effect. So we do see that damages have been increasing with time when it comes to extreme weather events. Now, there's a few reasons for, there's a few different theories for why that is. One of them is that our storms themselves are getting stronger, and that's a possibility. The other likely reason, it could go hand in hand with the other one as well, but is this thing called the expanding bullseye effect. So that's what we've been talking about a little bit in class, not directly, but our urban spaces tend to grow outwards, don't they? They grew upwards when we got the technology, but they've also been expanding outwards with things like transportation changes. So this black thing here would be a possible tornado track. And this will never move. It's in the same place the whole time. But let's say in 1950, it went through this rural urban area mostly, and then the other half was in this ex-urban and suburban area, right on the outskirts of that urban area. But then in 1980, that city's grown, and that same tornado, the same path that it took, would have hit part of the downtown, the most urban part. 2010, now almost the whole thing is in some form of ex-urban, suburban, or urban area. 2040, almost half of it's in that highly urbanized area. So the expanding bullseye effect is saying even in the absence of stronger storms, even if our storms stayed the same, because we're giving the storms more things to hit, we're going to see more property damage. So this is a summary of what I just said. So while the climate change that we see now might amplify the risk of certain hazards, the root cause of these escalating disasters is not necessarily event frequency or risk related. Rather, it's the increasing exposure and vulnerability of populations. We're putting ourselves in the way of these storms. So here's another example. This is based off the 2013 Moore, Oklahoma tornado. So you can see that in 1950 it would have been mostly in an exurban, whereas in 2100 almost half of it's through a very urban area. You would get a lot more damage in this case. Here's another example of the Washington, Illinois tornado from 2013. This is the November 17th, 2013 tornado. You can actually see the tornado scar on the landscape. And then we marked where that would have taken place in 1994. There's a lot less in the way. It wouldn't have hit as much as it did in 2013. This is also true for hurricanes and for flooding. So when we're talking about return period, this is an average of how often you can expect a hurricane of a similar magnitude to hit a specific point. So this is for any hurricane. So any hurricane is classified as winds 74 miles an hour or higher. So let's say right here, New Orleans, you can expect a hurricane every 7 years. This is old, probably should be updated. Here on the tip of Florida, also every 7 years. Out here, Outer Banks, 5 years. Georgia coast, 10 years. Northeast, you've seen 50 years. So these are changing with climate change, but I'm going to focus in on the Florida coast a little bit. So actually, first major hurricane, this is when you have winds 111 miles an hour or higher. Obviously, all the years went up a little bit. We went from 7 to 19. I want you to take note of our scale. Our scale changed. But we see the similar areas being affected. All right. So let's look at this area. This is what it looked like in 1940. This is in Florida. And as you can see, not much of it is urbanized. If the same hurricane that hit in 2020 passed through this area in 1940, not much would have been lost. But when it hit in 2020, you can see how rapidly this area has been urbanized. There's a lot of homes, businesses, vacation properties here, and a lot of this was destroyed by the recent hurricane that happened in 2020. This is just another effect of that expanding bullseye. And it also raises the question on insurance. If we have this return period, this average return period, where there's going to be a hurricane every 8-10 years, more now because of climate change, why are we still building in these areas? Is it worth it? I know the beach is very pretty and there's a lot of money to be made there, but if it's going to be destroyed, should we keep building there? And if we keep building there, our national flood insurance program is nationally funded. Should insurance be given to those people who continue to build in areas that are going to continually be destroyed by hurricanes? This is not a question that I intend to answer. It is something I want to pose to you to think about. Should people keep building in areas that they know will be hit by hurricanes or other natural disasters? That is all that I have for you guys. It is a very broad summary. All of these topics are covered more in detail in Dr. Shepard's urban climatology class. So if any of that sounded interesting to you, I highly encourage you to go check it out. It's a very interesting class. I learned a lot. That is all. Thank you very much.